I will begin. Heavenly Father, we thank you for this day. Thank you for the students. We ask you to bless our work today, Lord. In your name I pray. Amen. Okay, guys. So now that we're done with our daily dose of harassing Liam, let's see, it's mostly good-natured. Let's see, some of this he has coming. Let's see here. Let's see here. Let's see here. All right. So I don't know. I have tried to process Dummett and Foote in terms of like the Lagrange's resolvent cubic and all that stuff, but it's just I cannot quite come to a working understanding of it. So I thought it would be probably more beneficial for you guys for me to jump to another book and just write down what's going on, because it will get to the point a little bit faster. So I'm going to do that here. And here it is. So so he starts with y cubed, and I'm on page 434 to 435 of Introduction to Abstract Algebra by Nicholson, a book that none of you have. So sorry. Y cubed plus ry squared, but the this will be very much like what I talked about. Oops, plus t. So he starts with this, then he makes a substitution of y equal to x minus 1/3 r. That makes this equal to x cubed plus bx plus c, a so-called depressed cubic, right? And he says, okay, so since if we can find the roots for the depressed cubic, we can shift them to get the roots for the original cubic, we might as well just figure out how to find how to solve a depressed cubic, right? That was the big idea here. Okay, so we need to think about how to solve x cubed plus bx plus c equals to 0. How to solve this, all right? And so what he does is he says, okay, so suppose it has roots u1, u2, u3. So in other words, this can be factored into x minus u1, x minus u2, x minus u3, right? Now, he says the roots are related to the coefficients as follows. All right. So we're trying to solve this equal to 0. But what's the relation between the roots and the coefficients b and c, right? We can figure that out by direct hand-to-hand combat on the coefficients here, right? What is it? Let's see here. C is what? I'm going to put a minus on each one. Duh. Yes, like just what you said. Minus u1, u2, u3. What should b be equal to? Yeah, u1, let's see here. u1, u2, right? Like this times that, times x, right? And then we can think about this times that, which would give me plus u1, u3, right? And then we can think about this x times this times that, right? Which would give me plus u2, u3. Did I ever show you guys the video of the little boy drinking from the fire hose? To me, that's sometimes what I feel like in Dummett and Foote. They're just besieged by this, like, there's just so much. So this book has less, which to me is more in the current conversation. It keeps me focused here. All right, let's stay focused. What else do we got? And then this one, he says, yeah?
Well, is there sum equal to 0?
Yes, why would that be?
X times u1 negative u1. I guess it's their negative sum. Well, it doesn't matter.
So let me see here. So this is, yeah, oh, exact, thank you. This is the constant, this is the x, and this is the x squared coefficient. But, we can also look at this in terms of the symmetric functions, right? Symmetric functions of the roots. The other way to look at this, yeah. So you see symmetric functions of the roots going on there. All right, so we have this. Let's go on. He says, now, let omega equal to e to the 2 pi I over 3. All right, cube root of unity. So this has the omega cubed is 1. And of course, we also know that 1 plus omega squared is 0, right? And he says we're going to look for formulas for the roots of the form he says u1 equals to p plus q. He has not introduced p and q yet, has he? No. All right, u1 equals p plus q. u2, this seems a little bit unmotivated to me at the moment. u2 is omega p. This seems like dark magic. Not in a good way. q. u3. So we have u2, u1, u3 written like that. P and q are he says p and q are to be determined. He says the condition u1 plus u2 plus u3 equals 0 is automatically satisfied because omega satisfies the. All right. Why should we look at u1 and u2, u3 to be that form? I suppose, in fairness to Nicholson, I haven't read everything up in the book up to this point recently, There may be some sort of reason for doing this. Do you guys have any?
Well, that's just p. If you add u1, u2, and u3, that's just p times 0 plus q times 0.
If we add.
Because that's p plus p times 1 plus omega squared.
So u1 plus u2 plus u3 is 0 by your observation that it's the coefficient of x squared, but it's also what?
Right, it's also, so you can substitute in or whatever, since 1 plus omega squared is 0,
Uh-huh.
then you can substitute in, like you're just adding 2 zeros right there, for some p and q.
Ah.
That's what the motivation is there.
Huh. I see. I guess that gives you some sense. In my current reading, this is just an educated guess. Ansatz, like German for guess. So. What? Oh, sorry. This is a common terminology in You're like, no, it's not common. I'm sorry. Sometimes I forget I was raised by physicists. This is something they like to say. I mean, you can do a Gedanken. That's German for thought experiment. Let's see here. Anyway, so that is, well, okay, so this much we can say if we construct Q1 and if we do make this wildly unmotivated educated guess at the moment, which I'm willing to do, right, for the sake of ownership of the formulas, clearly it solves the third condition rather, this one, right? But we also want it to solve the B and the C condition as well, right? The constant and the x co. So what's that force upon us? Okay, so what I'm saying is check. What happens when we, which one should we do first? Want to do B? B equals to U1, U2 plus U1, U3 plus U2, U3. What's that work out to? U1, U2 is P plus Q. Yo. Maybe I'm going to regret this. Good night. There should be some sort of awesome factoring by grouping that happens or something here, right? Like if I take this P plus Q, right? And I take this omega P and this omega squared P, right? That gives me this. And I need a 1 here, right? And so that's 0. All right. And then I can play a similar game with this times this and this times that. And now I've accounted for everything in the first two products. And I don't know what happens over what?
Where did the 1 come from in the very first term?
I added and subtracted 0.
Oh, okay.
So these are, and the reason I'm doing that is to make the 0 appear.
Is there already a 1 somewhere in there because of like the next?
Oh, probably. I just did it that way. I mean, I'm probably just making it more complicated than it needs to be. If we just I'm just going to FOIL this thing out over here. What do you got? Omega cubed P squared plus omega squared PQ plus PQ omega to the 4th plus omega cubed Q squared. But remember, omega cubed is what? Omega cubed is 1, right? Omega to the 4th is omega. And so I've really got minus 2pq plus p squared plus q squared plus parentheses omega squared plus omega pq. Ooh. 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 Interesting. You guys have any suggestions on how to make that prettier? I would suggest that we can add and subtract. I mean, I don't like this. So to fix that, I will add 1, and I will subtract a PQ. Right? Because that is a way to get rid of omegas. And of course, this is 0, as were the two above. And so if you look at it, then what do we got? Looks like we've got p squared plus q squared minus 3 times p plus q.
Wait,
No? I could be wrong.
that is a minus PQ up there, not a P plus.
Oh. Thank you very much. Keep me honest, that's good, because otherwise it's not going to match the result. You know, math is funny that way. So we got what, minus PQ? Was what you're telling me, right?
Yes.
I guess that makes sense. I mean, it should be quadratic in P and Q because the U's were linear in P and Q, and we multiplied them, so it should be quadratic in the P and the Q. I mean, that the general sense of it makes sense, I think. Whoa. I mean, he says somehow this reduces, we can derive PQ as minus B over 3.
Oh, because it's times PQ.
Right.
Never mind, I get it.
Yeah. B over, I mean, what? You know? Is there, I guess we haven't, what have we not used yet? There must be some sort of secret sauce in the other, the other. Oi. Okay, so like U1 plus U2 plus U3 is not that interesting. That's like automatically true for the gas, right? There's nothing to be gained. But this C equation maybe is something. What is, but this just involves B. How does that simplify to PQ? Am I not seeing something that's just right in front of my face? Is this, what's going on here? Is this P squared minus 2 times P plus Q minus PQ plus Q squared? Can we factor that somehow? But I got the P 2 times P plus Q in the middle. So.
Yeah. If you have P minus Q and then square that, you would, oh wait.
I mean, we could factor a P out, you know. P times P minus 2, and then Q times, you know, Q minus 2, but we still got that pesky PQ sitting over here. That's not helpful. All right, I said it about 3 minutes ago. Let's actually look at the C condition, see if that, maybe that'll make something jump off the page at us. Yeah? Although you guys remember, for the quadratic last time, it was pretty easy to get lost. And that was a much, I mean, it has to do with looking for those patterns in the symmetric polynomials. It's that algebra. Okay, so what's C? What did we say it was? Minus U1 minus U2, which is minus P plus Q, omega P plus omega squared Q, omega squared P, omega Q. So we multiply this thing out, what do we got? So this times this gives me a P squared. This times that gives me omega squared PQ. This gives me plus omega QP plus Q squared. So I got minus P plus Q times P squared plus PQ times omega squared plus omega plus 1 minus PQ plus Q squared, playing my usual game, which may or may not actually be helpful for us, by the way. It could be that playing this game is what's making it impossible for us to see what we're supposed to see. I don't know. You know? I mean, something went bad. So I've got P squared minus PQ plus Q squared if I haven't made a mistake there. There's your C. And he somehow has minus C is P cubed plus Q cubed. P cubed plus Q cubed is minus C, according to him. Is it just a matter of me, like, multiplying? Am I almost there?
I'm pretty sure that's just the form when you like.
Just, oh, you're saying that this is literally,
I
oh,
think it's just
the trinomial special form trinomial that I'm supposed to.
Because, well, I think the negative in front is what makes the C negative, and then everything else makes it so that it's the
So that is that, because we get P cubed and then the minus P squared Q, but over here, the plus, oh, the stupid minus is messing with, okay, so let's see here, minus P squared Q plus QP squared, and then, yeah, so, right. Okay, well, we see that much. Hey, woo. Why is that minus B over 3? A mistake would be lovely. A mistake would be lovely, yeah. Because the mistake should be something like, some things should have been canceling and somehow giving us 3 copies of PQ, yeah?
Because it looked like if we could do away with that P plus Q somehow, we end up with negative B is equal to, or like negative 3PQ is equal to B.
That's what we want, yeah.
And you had that at one, like you didn't have that exactly, but you did have a minus 3 in front of that P plus Q, and so you realized that like, so that was why I was wondering if it was a mistake somewhere. If maybe something got thrown off.
Well, let's just go back to the start and just check my starting point, right? U1, U2, is this U1, U2? Okay, yep. Is this U1, U3? Yep. Okay, is this U2, U3? Looks like it. Did I copy down? Well, no, those are right. I can't see it at the. But I agree. There must be a mistake here, or the. No, the book is right. The book is right. You see it?
No, I mean, no, not yet. But I think P plus Q is supposed to be squared. No. How did you pull out? So for that very first thing, you said you pulled out. You added the 1.
Yeah.
Right in this. But how did you pull out the P and the Q from that first?
Oh, there's supposed to be a P with that.
Yes.
Ah, curses. Thank you. You have found my. Can I? Well. Oh, so this is there's supposed to be a P here, but also here, right?
So that there's a Q with the
And this one's supposed to have a Q here and here, or is it just not even that? I mean, this one,
I'm not sure.
the
I'm not
the blue, the
tracked with
okay. So the blue, I had a omega squared Q and omega Q, so I'm supposed to have a Q out here, and so I added and subtracted P plus Q times Q, and this over here was fine. So the long and short of that is, it makes this. Well, it's not. I need to erase. All right, so this is 0. We get minus P plus Q times P plus, or minus rather, P plus Q times Q. And then this stuff over here, which was what? We have a plus P squared, we have a plus Q squared from this one and that one. And then we have plus omega squared PQ plus PQ omega. So what cancels, of course, is this P squared cancels that one, this Q squared cancels that one, and that leaves us minus PQ minus PQ minus 2PQ, and over here we've got plus omega squared plus omega PQ, otherwise known as minus PQ. See, because we can trade omega squared plus omega for a minus 1 to get the last one.
Where did the minus 2 come from?
This and that. All right, so why does this help? Right? Why does this help? I mean, how does this help us solve the... Is it? I don't think it's yet obvious why this helps us solve, does it? Is it obvious to you guys? Not obvious to me yet. Let me put my other claim up here. So we figured out that this one, and also, what was it, C? Well, P cubed plus Q cubed is equal to minus C. So we've got, I'll put those up here so we don't lose them. All right. he says the following. He says, these equations imply that p cubed and q cubed both satisfy the quadratic equation, what? Here we go. These equations imply that p cubed and q cubed solve the quadratic equation x squared plus cx minus b cubed over 27 equal to 0. Is that, why is that? You see it?
Kind of, because that's b over 3 cubed, and, or minus b over 3 cubed, and that's p cubed. So the last one.
Can you elaborate on that? Wait, I'm sorry, I don't.
So the last term, the b cubed over 27, would just be
Uh-huh.
minus b over 3 all cubed, which is equal to b cubed all cubed. And so then it would just be, like that whole thing is x minus b cubed times q minus.
That whole thing is what?
The quadratic is x minus b cubed times q minus, or x minus q. I'm sorry.
Okay.
X minus q.
X minus, let me write down here, x minus p,
Not all cubed, just the p is cubed.
oh, x minus p cubed.
And then x minus times x minus q. Oh.
That makes a lot of sense because that is x squared plus, well, minus p cubed plus q cubed x plus pq cubed, which, like you just said, is x squared, and that was plus cx minus b cubed over 27. All right, great. Now we're in business because we have done what? We've traded our original cubic problem for the depressed cubic, and then now for a corresponding quadratic, right? And we can solve a quadratic equation. How do we do it? Let's see here. So we say, okay, so x is equal to what? Minus c plus or minus the square root of what? C squared. What? Minus, well, plus, I suppose, 4 27ths. B cubed, yeah. Divided by 2. So what does that do for me? So that tells me that P and Q, are equal to whatever. I mean, these guys, right? Well, yeah, thank you. I'll get it eventually. Thank you. But, so, but I don't, I have to be careful, right? So I find this I solve this quadratic equation, I take a third root of it, I call it p, right? Then how do I choose q?
So it's like one, the negative c plus the rest, and it's the other one,
Yeah,
negative c minus the other one.
right. But I think there's more to it than just that, right? Because I mean, yes, but when I take the third root, I have to take it in the complex sense, right? Like it might not be the principal third root, it might be a complex third root, and I have to be careful to make sure I mind the other relations going on here involving p and q. I'm not sure how that goes. Oh, well, I know that the product of p and q has to be minus b over 3, right? So that says that the way I choose the third root for q from the minus, if I choose the plus solution to get the third root, plus solution, take the third root, call that p. Minus solution, take some third root to call it q. I need to make sure I choose that third root for the q such that when I multiply pq, I get minus b over 3. Now b is real, right? So that means I think I need to choose the other third root in like the conjugate sense, right? Otherwise, the product of p and q won't be real. Or if I can, I choose a real third root for both of them. It's proved in Dummett and Foote that sometimes it's impossible to avoid taking a complex root here. There exists cubic polynomials. It is an absolute necessity to use complex roots in order to construct the real solution. This was very troubling for those people who thought complex numbers were some sort of artifact or, you know, whimsical things that king's mathematicians think of, not like real things like counting numbers or those slightly less, you know, believable negative numbers that people didn't entirely believe in the existence of at this sort of time period back then. I mean, here's what he says. He just writes it this way. He says, okay, so p is equal to 1/2 minus c plus the square root of c squared plus 4/27 b cubed 1/3, and q equals to 1/2 minus c minus the square root of c squared plus 4/27 b cubed third root, such that the cube roots are taken such that pq is equal to minus b over 3. So he just says that in this book. What's the discriminant here? Yep. So the discriminant, he uses a delta in this book for it. It's minus 4 b cubed minus 27 c squared. So I guess you have to, it's not quite, it's related to it, but.
Yeah, because that's the discriminant for the quadratic, right? Just if you just take what's in the radical.
Right. It just so happens that the discriminant for the depressed cubic is minus 4b cubed minus 27c squared. Can you see that? I think this is the square root of minus, this would be the square root of minus delta, wouldn't it be, in the current notation? Did we write this down for Dummett and Foote? I can't remember. The discriminant for the cubic, for the depressed cubic.
We wrote it down, yes.
What was it? It was that?
Yeah, just four.
Oh, Dummett and Foote also used the B and the C just like this?
Well, he's a P and Q.
Up.
Just B is P.
P and Q. Most unfortunate choice of letters.
Okay, so is the symbol for discriminant a triangle?
In this book, yes. But in Dummett and Foote, it's D. It's big D. Sorry, I'm having a moment of stupidity. If I factor a 27 out of this, I get 27c squared plus 4b cubed, right? So, well, anyway, whether this is 0 or positive or negative will influence the kind of cubic solution you're looking at. And this is discussed in you know, pretty great depth in Dummett and Foote in terms of what happens when that's 0 versus not 0. And he proves that not only does it appear that you need a complex number, it's unavoidable for certain cases of the cubic equation, which is, you know, again, kind of shocking because you might think that at least if you focused your attention, right, on cubic equations which have real solutions, only real solutions, you might be tempted to think that you can write down a cubic formula which does not use complex numbers. It is proved in Dummett and Foote that is not the case. There exist cubics which unavoidably use complex numbers in their solution in terms of roots. So this is kind of old news. Here's the bit of history. Nicola Tartaglia rediscovered this. So this cubic formula was, I guess this was Del Ferro, 1465 to 1526. Found this, and then Tartaglia discovered it again and published it Cardano published it in 1545 in the book Ars Magna, and that book also contained, I can't say any of these names, Ferrari's method for solving quartic equations, and then of course that sort of set the stage for the great 18th century mathematician Lagrange trying to generalize their method for depressed cubics to solve it by essentially the same bag of tricks. And then you see the ultimate result of that is like the Lagrange resolvent and those things you see in Dummett and Foote. That's just the tip of the iceberg there, of that machine that Lagrange built. And by the time of the turn of the 19th century came along, people were relatively convinced that, well, if Lagrange can't do it, what are the odds that anybody else can, So, proof by Lagrange can't do it was the standing proof at the turn of the 19th century. But then Ruffini in 1813 published something that people still don't believe, but talk about for some reason. And then I think the first convincing no-go, you can't find a general quintic equation, was by Abel, depending where you're from, in about 1820. And then Mr. Galois, yeah, Galois came along 1830 or so, and not only proved that, Abel had already proved it couldn't be done, but Galois proved that sometimes it can be done, and here's where you can do it in terms of calculating the Galois group and using the solvability. Now, how that solvability actually leads to a computation and how to solve in terms of radicals in the extension, that I haven't really taught you. It's explained some in Dummett and Foote, but this is kind of where we get to in here. I will say this, that thing I showed you guys with Bill's PDF, calculating the norm, I tried it out for a quartic extension, so like extending by, take Q adjoin root 2 and root 3, and I tried rationalizing like 1 over like 1 plus the square root of 2 plus the square root of 3, and it worked. It wasn't that bad, actually. It's kind of neat. So, I don't know. I think there's a lot of fun problems that could be invented based on playing with that norm idea we showed you. But that's where I am currently in my understanding of it. I will not attempt to show you the quartic formula. And I still don't understand how on earth my wife did this in high school in Hong Kong. What is right? Yes, they solved the cubic and the quartic in high school.
And the quartic.
Yeah. Not from Galois theory, obviously, just from like just brute force substitution and manipulation like this, yeah. Quote unquote A-level mathematics in Hong Kong. Anytime you hear US students say, okay, do this too hard, just say shut up. Just shut up. Anyway, what were you saying?
Did you say that if a cubic has all real solutions, you might have to go with the complex numbers?
Yes, right.
Okay. I just
Yeah.
want to make sure you're saying all
That-
real solutions, but still have to go.
Yeah, they can be that all of the roots we're looking for are real, and still the inner workings of the solution by radicals still inextricably complex. Yeah, it happens. Sorry, I haven't actually worked a problem with numbers today. I mean, I'd like to do that. I just didn't. I've been trying to get to that point of having that ready for you today. It didn't happen. So Wednesday, I need to go to. I should really go to King's talk in the research week. It's supposed to be at 2. How long are the talks, Bethany? 50 minutes, 5 minutes. So that means that should finish at 2:20, which means we should still be able to have class starting at, let's say, 2:30. So we'll have a half-hour class. We'll be doing the differential. So I'll start talking to you guys about differential algebra.
And because that's at the end of the mission, is that still due Wednesday?
It should still be. I think it should still be due Wednesday. I'll try to. Those questions are really. There's nothing computational in there. That's just storytelling. And so I'll try to tell the story this week to get to the point of answering those questions. I won't prove everything in those. So I'll post 2 PDFs that my brother wrote on differential algebra. It's very interesting. What it amounts to is looking at another analog to Galois theory, which answers questions of like. You remember when you're taking integration, you always wondered, could you integrate this function in terms of elementary functions? This is the algebra which gives a definitive answer one way or the other on that. It proves that the integral of e to the x squared cannot be written in terms of a product, sum, whatever, of elementary functions. So I think it's neat. But it would take us a whole semester to get computationally where we need to be on it. But I think you guys will understand it, at least from a kind of fuzzy perspective. That's all I'm going for the next hour and a half or so. Thanks, guys.